Imagine that in this world there is a hidden presence, an unseen force that influences everything around us. Without it, galaxies would fly apart. The world as we know it would simply not exist. Well, this could all be true. Thanks to the latest developments in quantum technology, a new generation of scientists have joined the hunt for the existence of dark matter.
So I'm Professor Jocelyn Monroe at the University of Oxford in the Department of Physics, and I'm an experimental particle physicist doing experiments looking for dark matter.
Can you explain to us, as simply as possible, what is dark matter?
I wish I could tell you the answer to that question. We don't know what dark matter is. We know from astrophysical observations that there is a dominant component of all of the matter in the universe that doesn't interact with light, but it does interact via gravity. So we can see evidence of dark matter's gravitational interactions with things we can see, like stars, galaxies, but we can't see the dark matter itself.
Can you give an example of what kind of gravitational effects we see that tells us dark matter's out there?
The very first observations of dark matter were made in the 1930s by looking at the motions of galaxies in galaxy clusters. By looking at the velocity at which those galaxies are moving, one can infer the amount of mass that's interacting gravitationally. And in fact, that kind of measurement, inferring the mass, implies that there was roughly 500 times more mass interacting gravitationally than what you would predict based on adding up the brightness of all the objects you could see. There are measurements that were made in the late 1970s by Vera Rubin, looking at the speed with which stars are rotating around the center of the galaxies that they're bound to. And if we write down, using Newtonian mechanics, what we expect for the velocity of those stars, what we see is very, very different. It disagrees with that prediction. And you can resolve that contradiction by positing that actually the luminous part of a galaxy that we can see sits inside of a much, much larger halo of these dark matter particles, which are interacting gravitationally, pulling on that star, but not interacting with light, so we don't see them.
Where is dark matter?
Everywhere.
Everywhere?
In this room, right now.
Okay. Gosh.
We don't know what it is. Passing through you at this very instant.
Hi, I'm Ed Dorr, and I'm a professor of physics at the University of Sheffield. We use very sensitive quantum sensors to try and probe new hypothetical particles which could play an important role in astrophysics and cosmology if they exist. And so we've got this collaboration which is building new detectors to look for these kinds of particles using new technology which we're also along the way testing and characterizing.
What is an axion?
Axions are one possibility to explain this dark matter, and potentially they show up in enormous numbers shortly after the Big Bang, and they're still here. Since then, they've just been hanging around.
How do we hunt for axions?
So axion, when it decays, one of the only things it can do is decay into 2 photons. But it does that incredibly rarely. So if you sit an axion on a table and just wait for it to decay, you'll wait 10 to the 34 years on average. And the way you accumulate them is with a cavity. So what we do is we take our cavity and we turn it into a quiet place. And the way we do that is to cool the walls of the cavity. So this piece of equipment behind us is called a dilution refrigerator, and its job is to make a very cold place. Very simply, that plate at the bottom of it gets down to a temperature of 1/100th of a degree centigrade, above absolute zero. What really brings the odds up is supplying a magnetic field. Now, when a magnetic field, an axion can interact, it can literally scatter off the field and produce radio waves. So what happens is the axion essentially rams into the magnetic field, converts its matter into the energy of a single photon. That photon ends up causing the cavity mode to gain a little bit of amplitude. It gains 1 quantum of excitation. And then another axion comes along and it pumps it up a little more. So they generate what I call standing waves in the cavities. Now the difficult bit is actually detecting that standing wave vibration using external electronics. And what you're doing is detecting the amplitude of the mode inside the cavity using a whip antenna. It's essentially just a metal bar that's connected to the input of your electronics.
When this radio frequency is picked up by the antennae, how is it then read out by scientists at room temperature?
Right, so the first thing you do is put it through a very low noise amplifier. And the job of the amplifier is to make the signal bigger without adding too much noise. And then once the signal's bigger, you amplify it some more, which makes it even bigger. And then finally you get up to room temperature. Now convert the signal as a function of time into a signal where you're looking at frequency instead of time. That's called spectral analysis. The frequency of the resonance has to match the axion mass, and you don't know the axion mass, so you have to be able to tune the resonance. And the axion shows up as a peak in that signal.
Are you trying to basically build the world's most sensitive radio?
Yes.
Okay.
Initially, it's the world's most sensitive AM radio. One day it might even be FM as well.
So I'm a low temperature physicist working at Lancaster University in the physics department and in the ultra low temperature physics group.
What is a WIMP?
Okay, a very good question. So WIMP stands for the weakly interacting massive particle. There's a good chance that the dark matter in our universe is made of WIMPs.
How do we hunt for WIMPs?
Well, we as humans cannot smell them, cannot see them, cannot feel them. So we need to build some apparatus which will be a lot more sensitive than us humans. Before hunting for WIMPs, we need to make some assumptions about what they are. Well, suppose they were NIMPs, non-interacting massive particles, then it would not make any sense to hunt for them because they don't interact with anything. So we do assume that they interact with normal matter, the atoms, the materials that we use in everyday life.
So, if WIMPs are so weakly interacting, how then do we build a detector to detect them?
If the WIMPs are light enough, so their mass is a mass of a few protons, we choose our target atoms to be of the similar mass of the WIMP. In our case, this is the helium atom, one of the lightest ones. Our atoms are more likely to be moved by this interaction. So the apparatus that we use in our experiments is a small box, just a fraction of a cubic centimeter in size, which is filled with superfluid helium.
What is a superfluid?
Superfluid means that the atoms are in the same quantum mechanical state. And in this ground state, the atoms move very, very slowly indeed. And inside this box, we have a vibrating nanowire. And when we see that a particle or a WIMP collided with one of the helium-3 atoms, and it will be an avalanche effect essentially. So it will actually set in motion billions of atoms, which start moving chaotically inside this box. These atoms collide with our vibrating nanowire and its vibrations slow down. And we can see that from the electromagnetic signal we pick up from the vibrating nanowire. And this is how we know that the WIMP interacted with one of the atoms in the superfluid.
How would you celebrate the discovery of dark matter if it comes to it?
How would I celebrate? Goodness.
God, I haven't even thought about it.
Well, that's a very good question.
No one
What a
really knows
question.
until it happens.
I
right?
mean, I think I'd call my mother, first of all.
Yeah.
And then immediately after that,
We'd have a big party with lots of music.
Okay.
Probably not in here. It's like, we'd go somewhere else.
Go to the pub with friends and colleagues and celebrate.
Don't forget to invite me.
I would probably celebrate by putting in, you know, an enormously ambitious proposal to build a detector 1,000 times bigger. You know, that's after the champagne-fueled party and the, you know.
Yeah. Why do we hunt for dark matter?
I'll give you two answers to that question. I think, you know, the first one is that we know at this point that dark matter makes up most of the matter in the universe, and we'd like to know what it is. So sheer scientific curiosity.
Makes sense.
The second answer I'll give you is I think that this pursuit of knowledge about the fundamental properties of particles has been shown historically to have great benefit for humanity. When J.J. Thomson was studying the quantum mechanical properties of the electron, he didn't know that 50 years later, the transistor would be based on the quantum mechanical properties of that particle. And he didn't know that 100 years after that, we'd all be walking around with a device in our pocket, with 100,000 transistors that's totally transformed the way we live our lives.